Welcome to today's paper reading. Today's paper is titled 3DGS-LM, Faster Gaussian-Splatting Optimization with Levenberg-Marquardt. This paper was published on AR14 by Lucas Hollian and colleagues from Technical University of Munich and Meta. The 3DGS-LM method introduces a significant improvement in the reconstruction process of 3D Gaussian splatting by replacing the traditional atom optimizer with a tailored Levenberg-Marquardt (LM) optimizer. This change not only accelerates the process, but also maintains the same high level of reconstruction quality. The optimization strategy involves the use of an LM optimizer, a caching data structure designed to handle intermediate gradients efficiently, and custom CUDA kernels for the calculation of Jacobian vector products. These enhancements result in a 30% increase in speed compared to the original 3DGS method. Additionally, the optimization approach is agnostic to other methods that might further accelerate 3DGS, potentially leading to even greater speed improvements. Figure 1 illustrates the acceleration of 3D Gaussian splatting, 3DGS, reconstruction through the replacement of the atom optimizer with a tailored Levenberg-Marquardt. On the left, it shows that starting from the same initialization, our method achieves a 30% faster convergence on the tanks and temples, train, scene. On the right, it demonstrates that after the same amount of time, our method yields higher quality renderings, characterized by improved brightness and contrast. Novel view synthesis, NVS, is the process of rendering a scene from new viewpoints using a set of input images. This technique is crucial for achieving photorealistic immersion in virtual reality applications, allowing users to explore captured scenes freely. Among various 3D scene representations, 3D Gaussian splatting, 3DGS, stands out. It represents the scene as a set of 3D Gaussians, enabling real-time rendering and high-quality image synthesis. The 3DGS method is optimized from a set of posed input images through a differentiable rasterizer, where Gaussians are updated using gradient descent. This optimization process can be resource-intensive, often taking up to an hour for high-resolution datasets. In recent years, novel view synthesis has been widely explored, with neural radiance fields, NeRF, and 3D Gaussian splatting, 3DGS, being particularly successful. NeRF optimizes MLP weights through volume rendering, while 3DGS represents scenes as 3D Gaussians for real-time rendering. Various methods have aimed to speed up these processes, including using neural network priors for sparse view reconstruction and improving the differentiable rasterizer. Our work focuses on dense view and per-scene optimization, employing the Levenberg-Marquardt algorithm with a caching data structure to accelerate 3DGS optimization. Figure 2 illustrates our method for accelerating 3D Gaussian splatting, 3DGS, optimization. The process is divided into two stages. Initially, we utilize the atom optimizer along with a densification scheme to establish an initial configuration for all Gaussians. This step provides a solid foundation for the optimization process. Subsequently, we transition to the Levenberg-Marquardt algorithm to finalize the optimization. This two-step approach ensures efficient and effective optimization of the 3DGS, enhancing both the speed and quality of the reconstruction. The two-stage 3DGS optimization pipeline begins with an initialization stage where Gaussians are densified using the 3DGS model combined with the atom optimizer. These Gaussians remain unconverged at this point. The second stage involves the optimization process, where the LM optimizer, implemented in efficient CUDA kernels, is used to accelerate convergence. Key features of this stage include the use of the Levenberg-Marquardt algorithm, a memory-efficient precondition conjugate gradient (PCG) implementation, and an image subsampling scheme to manage GPU memory usage. Figure 4 illustrates the comparison of initialization iterations in our method. Initially, we use gradient descent to initialize the Gaussians for k iterations, followed by fine-tuning with our LM optimizer. Our method demonstrates faster convergence after 600 or 8,000 iterations compared to the baseline. Conversely, using fewer iterations results in slower convergence with pure LM, emphasizing the significance of our two-stage approach. These results are reported on the garden scene from MIPNRF 360 without densification. The LM optimizer was compared against Atom using multiple reference implementations of 3DGS. This comparison includes the original 3DGS implementation, its reimplementation Gaussian-Splatting, and Indepth. Additionally, taming 3DGS was included by utilizing their release source code. All baselines were run for 30K iterations with their default hyperparameters. The datasets used for benchmarking include tanks and temples, deep blending, and MIP-NRF 360, which contain 13 scenes covering various environments. Quality metrics such as PSNR, SSIM, and PIPS were used, along with optimization runtime and GPU memory consumption. The implementation details show that the first stage runs for 20K iterations, densification completes after 15K iterations, and only 5 LM iterations with 8 PCG iterations are needed to converge on all scenes. Figure 5 presents a qualitative comparison between our method and various baselines in terms of rendered test images after similar optimization times. The key observation is that all baseline methods converge faster when integrated with our LM optimizer. This improvement is visually evident in the rendered images, which exhibit fewer artifacts and more accurate brightness and contrast levels. This comparison underscores the effectiveness of our LM optimizer in enhancing the quality of rendered images while maintaining or improving convergence speed. Figure 6 presents a detailed runtime analysis of one iteration of our Levenberg-Marquardt LM optimizer, focusing on the computational steps involved. The runtime is primarily consumed by solving the preconditioned conjugate gradient, PCG, and building the cache, as highlighted in the figure. These operations are critical and significantly more time-consuming compared to other steps such as sorting the cache, rendering images, and performing line searches. The analysis is conducted on the garden scene from MIP-NRF 360 after densification, providing a real-world context for the performance metrics. The use of a per pixel per splat parallelization pattern in the PCG execution is noted, which involves running the ApplyJ and ApplyJT kernels up to 8 times. In contrast, the build cache kernel, which is executed once and parallelized per pixel, offers only a marginal speedup. This observation underscores the efficiency gains achieved through the proposed caching structure. The figure also references a detailed profiling analysis of the kernels provided in the supplementary material, offering a deeper dive into the computational intricacies. Table 1 presents a quantitative comparison of our optimization method against several baselines. The key finding is that integrating our method with existing baselines results in a 30% reduction in optimization time while maintaining the same quality of results. This efficiency gain is particularly notable across different datasets and methods, indicating that our LM optimizer can be seamlessly integrated into various existing optimization frameworks, thereby offering a significant runtime improvement without compromising on quality. Table 2 presents an ablation study comparing the use of L1/SSIM losses against the L2 loss in optimization. The study shows that for both 3DGS optimized with Atom and combined with our method, the L1/SSIM objective yields better results and accelerates convergence. The results are reported on the garden scene from the MIP-NRF 360 dataset, starting from the same initialization. This comparison highlights the effectiveness of the L1/SSIM objective in improving both the quality of results and the efficiency of the optimization process. Table 3 presents an ablation study on batch size, varying the number of iterations, #I, and the number of images in a batch, #B. The study shows that decreasing the batch size, #B, for our method significantly reduces runtime and memory usage, with only a minor impact on quality. This indicates that image subsampling, as described in section 3.3.2, is effectively compatible with our LM optimizer. In contrast, increasing the number of iterations, #I, for 3DGS optimized with Atom results in slower performance and lower quality compared to our LM-based approach. The results are averaged over the NRF synthetic dataset, starting from the same initialization. This highlights the efficiency of our optimizer, which, by solving the normal equations in EQ2, makes higher quality update steps per iteration compared to Atom, which only utilizes gradient direction. The 3DGS-LM method presented in this paper accelerates the reconstruction of 3D Gaussian splatting by replacing the atom optimizer with a tailored Levenberg-Marquardt algorithm. This method, combined with a data parallelization scheme, allows for the efficient solution of normal equations using preconditioned conjugate gradient (PCG) in custom CUDA kernels. Employed in a two-stage approach, this leads to a significant 30% runtime acceleration compared to baseline methods. Additionally, the approach is shown to be agnostic to other methods, further enhancing the optimization runtime. The authors believe that this faster reconstruction capability will open new research avenues and make 3D Gaussian splatting more practical for a variety of real-world applications. The project was financially supported by several key sources. Firstly, it was funded through a research agreement sponsored by Meta. Additionally, the project received support from the ERC Starting Grant Scan 2 CAD, which has the grant number 804724. The German Research Foundation, DFG, also contributed through its research unit focused on learning and simulation in visual computing. The authors acknowledge valuable discussions with Justin Johnson from an earlier project with similar objectives, and with Peter Cochise regarding image subsampling. Angela Dye provided assistance with the video voiceover, which was instrumental in the project's communication efforts. Thank you for watching.